In most applied AI evaluation settings, you have access to a cheap proxy, like an LLM judge, and an expensive oracle, like a human expert. You want to use the cheap judge at scale, but here's the problem. Without calibration, higher judge scores can actually predict lower oracle scores. When this happens, rankings can flip entirely, and you can end up shipping the worst variant. Think sycophancy. Your absolute right likely scores high on cheap judges, but low on long-term user value. When our proxy points in the wrong direction, we leave ourselves open to all kinds of bad behavior. Susan Athey and some other prominent statisticians and economists developed a framework called the Surrogate Index for exactly this type of problem. Their work focused on combining short-term proxy metrics to estimate long-term treatment effects more rapidly and precisely. Causal Judge Evaluation, aka CJE, adapts this to LLM evaluation with one key addition: an auditable transport test that transforms a brittle assumption into something that can easily slot into the workflow of any applied evaluation practitioner. Let me show you. Let's start off with some policy evaluation basics. First up, what is a policy? If you've ever run an A/B test, you already know. Each cell in a randomized experiment is a policy. Testing blue button versus red button variants in an A/B test is effectively comparing the performance of two policies. When you ship software that uses LLMs, you're always faced with several decisions about how to configure your system. What prompts should you use? What model? What tools should your agent have access to? Ideally, you'd like those choices to maximize the outcome you care about, something like long-term user value. This is fundamentally a policy evaluation problem, where each candidate configuration corresponds to a policy you'd like to evaluate. In short, a policy is everything that shapes the action or response, except the user's input. Now let's get back to CJE. To make this precise, we need 5 objects in a causal DAG. X is the prompt or conversation history. Pi is the policy, the full system configuration as we just discussed. A is the answer the LLM system returns, what the policy produces given the prompt. S is the cheap judge score, an LLM judge, a heuristic, something you can run at scale for fractions of a cent. Y is the expensive oracle label. For example, like human expert annotations or a long-term user outcome you're willing to treat as ground truth. When we draw the causal mapping, here's what we see. X and pi both influence A. In other words, prompts and policies shape responses. X and A both influence S and Y. In other words, the judge and oracle consider both the prompt and the answer before generating a rating or label. S and Y are parallel measurements of the quality of A, where S is doing its best to approximate the expensive judgments of Y. But there's still one more variable, E, the environment. User population, time period, domain, anything that might shift between where you calibrate and where you deploy. Here's the key. We add dashed edges from pi and E into the calibration. These represent the possibility that the relationship between S and Y may differ across policies or environments. Those dashed edges represent the heart of the problem. You calibrate a judge today, but the mapping between S and Y is dynamic. Users shift, domains shift, and people get tired of certain behaviors like sycophancy. Calibration may change. That's the mechanism shift problem, and it's the reason naive judge evaluation can fail silently. In the ideal surrogate index story, you assume an invariance condition. Once you condition on S and X, neither policy nor environment carries extra information about Y. That's exactly what can break under policy or environment shift. So CJE doesn't assume it, we audit it. When we learn a calibration in one policy and environment and apply it to another where we have Y labels, do the residuals center around 0? If they don't, our results are biased. We'll explore this in more detail later, but first let's walk through the CJE pipeline. Now let me show you how CJE works. Here's the mapping. In Athey's surrogate index, T is the treatment, S is the surrogate, and Y is the outcome. In CJE, pi is the policy, S is the judge score, Y is the oracle. Same structure. So what is S exactly? It can be just a raw LLM judge score, or it can combine the judge score with other cheap features like response length. But keep it simple. Small oracle slices can't support many covariates. Here's the pipeline. Step 1, fit the mapping from S to Y via isotonic regression. This is your calibration model. Step 2, evaluate policies by applying the mapping to abundant S at scale. Judge scores are cheap, so you can estimate this precisely. Step 3. Audit transport in the target. Check whether your calibration still holds where you're using it. CJE makes calibration auditable, not just assumed. Let me show you the math that makes this work. The residual is the oracle minus the calibrated prediction. When you train your calibration in one setting and apply it to predict Y labels in another, the residual is what remains after you subtract your prediction of Y from what you actually observe. Here's the key identity. The expected oracle label, in other words, the average performance of the policy, equals calibrated prediction plus average residual. So everything hinges on one question. What's the average residual in the target setting? If it's 0, your calibration transports. Surrogate evaluation is unbiased. If it's not 0, you're systematically off, and the average residual tells you the direction and magnitude. The reason this matters is that the mean residual is auditable. Collect a few expensive oracle labels from the target policy as an audit slice. Apply the mapping you learned from your original setting to predict the audit slice labels. Measure the residual. If it's near 0, your calibration transports. In other words, you can trust the evaluation. If it's not near 0, you know exactly how to correct it. It's important to note that the audit slice must be held out from the learned calibration. Otherwise, the residual test is meaningless. Here's a quick and easy bias correction. Your estimate equals the calibrated prediction from the chief judge calls plus the average residual from the audit slice. Now let's see what this looks like in practice. Here's policy A. The residuals scatter around 0. Transport passes, meaning that you can safely use the calibration you learned from another setting. Here's policy B. The residuals are negative on average. The policy received high judge scores, but the oracle disagreed. Mean residual is not 0. Transport fails. This is what Goodhart looks like in the residuals. In other words, the policy learned to game the metric without creating real user value. CJE makes it practical to aim your evaluation at an expensive but trustworthy oracle. Calibrate cheap judge scores against a small oracle slice. 5 to 10% is often enough. Apply the learned calibration to evaluate at scale. When the stakes are high, audit whether that calibration still holds where you deploy. In our paper, we evaluated this approach on 5,000 prompts from the Chatbot Arena benchmark. CJE achieved 99% pairwise ranking accuracy at a 14x lower labeling cost as compared to using purely oracle labels. We also found that calibration learned from one policy transported cleanly to the others, except for an adversarial policy designed to be deliberately unhelpful. The lesson is intuitive. Transportability is more likely when comparing similar policies than radically different ones. LLM judges are an incredibly powerful tool for scalable AI evaluation. CJE leverages mature statistics to efficiently anchor the judge to what we actually care about. If you want to save money on labels and ground your evals in statistical guarantees, check out the Python package. It's open source, MIT licensed, and pip installable. Check out the paper on archive and the documentation at simolabs.com.